So the following page is probably one of the most important pages that you should look at for the entire semester. Everything that we do in finite element starts with what's called a weak form. So if I scroll back up, so we have this equation here. Here's our ODE. So this is ultimately what we're after. We want to solve this given a set of boundary conditions. This equation, this ODE, is in what's called a strong form. So at every point we're trying to satisfy this to be 0. In comparison to a strong form, okay, hang on. So if I come back up to here, in comparison to the strong form, basically this integrand, the weak form of that equation is this integral. So whenever I talk about a weak form, I'm talking about this integral here. And if we can make this be 0 over the entire bar, then we have a true solution. We can manipulate this using some math tricks, particularly integration by parts. So go back to your calculus book, look up integration by parts. You'll find something that looks like this. We're basically going to apply that to the finite element problem, and first I multiply my weight function. Remember, this is a weighted integral, so this is some function of x. I multiply that through both components. We're going to simplify this for right now. We're going to let this constant, let this be a constant. It doesn't necessarily have to be, but for purposes here it's just going to be a constant, so we don't differentiate. It comes out. Now we have to deal with this term, the second order derivative. This term we'll just carry it through. So if you look at this, we can do another math trick and use the product rule, where I take w du dx, I differentiate the whole thing, I get this term and this. So this is what's inside the integral, right? So I just rewrite the equation, I bring this over, I bring this over, and now I can substitute this part into here. So I substitute it back into the integral equation, I get something that looks like this. This is actually fairly simple. You can actually explicitly integrate this such that you only have this on the endpoints. So I can integrate over this relation, and I just have to evaluate w of x and du dx at the endpoints. This is the part that's unknown. This is what is the essential piece of the finite element problem. We want to solve this over the whole domain from 0 to L, subject to a set of boundary conditions. Now, more specifically, these boundary conditions are what's called natural boundary conditions. Though these boundary conditions are based on gradients in your solution. So you have du dx times a at the end. Remember, we've already defined this to be a flux. For a mechanics problem, this is your force. So if you know your force, you just substitute that in, and then you have to deal with this integral. So we'll talk about how to deal with this integral within the finite element method in the next few lectures. And we'll get into why this weight function is 1 by definition also.